Hello everyone. In this video, we will talk about two things. The first one is state information diffusion and distance factor, which is how the information is propagated and how it influences the distance factor calculation in each node through iteration. And then we'll talk about how the change of cost paths affect the update of information. And then we'll find one issue called the count to infinity problem. Okay, so first one, we'll talk about state information diffusion. Through iteration, the computation steps diffuses information through network. So let's have a look at the example below. So let's say we start the computation from C when at t equals 0, the state at C is only at C. Okay, and at t1, the information has propagated to next hop to B, and then it may influence the calculation of distance factor at B, okay, or one hop away. And at t equals 2, the information or state has propagated to two hops away, which is to A and E now from B. Okay, so it may influence the distance factor computation, not only at B but also at at A and at E as well. Okay, and then at t equals 3, the information or state from C has propagated from A to D, and from E goes to D, F, and H. So basically, we have three more nodes that can be influenced by the state at C. Okay, at state at C at t equals 0. Okay, so D, H, and F, as well as E, B, and A. Okay, and finally at t equals 4, um, the state at C at at t equals 0 has propagated to also G and I. So basically, at t equals 4, the state at C when t equals 0 has propagated to all the nodes in the network. So and this is also like, I mean, this is just we talk about when state at C when t equals 0. So when t equals 1, there may be some changes in C, and then it has been propagated to all the nodes as well. So this and from this example, we can see that it takes 4 iterations to for the information to go through all the networks. Okay, so when we talk about, okay, when t equals 1, then it takes again another 4 iterations, that all the information from C at t equals 1 propagated to all the nodes in the network. Okay, now let's talk about link cost change in distance factor. There are two, we can call there are two cases. The first one is when the link cost path change from a bigger one to a lower one. This is called the good news travel fast. Okay, so there's no issue about that. If node detects local link cost change, okay, so for example, y detect that link cost change from y to x, so it updates its dv and informs its neighbors. Okay, and then so at t1, Z updates receive the notification from Y, and then it updates its table and computes the new list cost to X. So if before, let's say at Y, the dyx equals 4, then due to the changes, it becomes 1. Okay, and then this information is propagated to Z. Okay, and dz x, initially it was 6, and now with this update, then it becomes only 2. Sorry, it was 5. Okay, it was 5, then it is updated to only 2. And then in the next iteration, or in the next timestamp, that dz also updates its own dv to neighbors y. But then, since there's no changes in the y's distance factor table, so this change stops here. So basically, there's not so much changes in the updates. Okay, so what happens when the link cost the link cost change from from a low number to a bigger number, or from good to bad, or the worst case is when it changes to infinity, or let's say the link is broken. Okay, so this is called the bad news travel slow, and it leads to a count to infinity problem. Okay, so let's have a look at this example. So first of all, y is direct link to x has new cost 60. Okay, so what is the initial distance factor at y? So initial distance factor at y is, let's say, at t equals 0, or yeah, okay, let's say at t0, dyx is 4. Okay, it was 4. And then also it knows that from z, the z dzx was 5. Okay, so this is just within the distance factor at y. But then, since it knows that there is a change in the link cost at this path from y to x, it becomes 60. So this direct path is no longer a preferable path. Okay, so it says that, okay, so the path from z to x equals 5. Okay, so it thinks that, okay, so I think it's better if I go to x through z. Okay, so this leads to change in the calculation of dyx, okay, at y. So now, instead of I'm going directly to x, now I think it's better to go to y, to x through z. Okay, so this becomes 5 plus 1. Okay, so if I'm formulating it to the let's say to the formal one, so this becomes minimum of um, dyx. Okay, and this is direct path, and dyz plus dzx. Okay, so if I'm taking direct path, it becomes 60. Okay, but if I'm taking this path through z, then okay, I know that the path to z, the cost is 1 plus 5. Okay, so now let's stop here at the moment. Why this, not why, okay, think that, okay, so I'm better to go to z. Okay, this although actually z, the cost of y to x, from z to x equals 5, because it goes through y also. Okay, but then the thing is, y doesn't know what is the path taken by z. Okay, the only thing that it knows is that, okay, so the path from y to z is 1. Okay, this is the path from y to z, from itself to z. And the other thing that it knows is the cost path from z to x is 5. Okay, it doesn't know whether to go to z, from z to x is also going through y. Okay, so this information is unknown from y itself. Okay, so that's why it thinks that, okay, so I think I have to take this path. Okay, so then it updates the cost path to 6. Okay, so now let's have a look at the next iteration. This send the updates of new dv to z. Okay, and z says, okay, so now the cost path from y to x has been updated to 6. Okay, so accordingly, then I have to update my cost path from z to x. So okay, so because it knows that the cost path from z to y equals 1, okay, so if the cost from y to x becomes 6, then the new cost path from z to x, okay, to x becomes 7. Okay, this is just to continue the process. Okay, now since z updates its own dv, so it propagates its changes to, or it's notify the change to its neighbors. Now in the next iteration, y receive these updates from z. Okay, so it knows that, okay, now the cost path from z to x becomes 7. Okay, the new cost path from z becomes 7. So again, if we take the same mechanism like this, now we simply update this to 7. Okay, and then y updates its own distance vector from y to x to becomes 8. Okay, now since there is a new change in this y's distance vector, so it sends the notification to neighbors, and eventually it is received by z. In the next iteration, z updates its distance vector from z to x. So if it was 7, now since the new cost path from y to x becomes 8, so then it updates it to 9. So and so on and so forth until it reaches eventually it reach the 60 from y to x, and from z to x it becomes 61. So this iterative process happens like, you can just count it yourself. It's from 4 or from 4 to 60. Okay, so this is a bit tricky for distributed algorithms. Okay, so finally we'll talk about the comparison between link state and distance vector algorithms. In terms of message complexity, as we have discussed in the previous videos about link state algorithms, for n routers it has n square complexity, and for distance vector, the exchange between neighbors, basically it's only exchange between neighbors, but then convergence time varies depending on the, well, depending on topology. Okay, it's not just depending on the number of nodes, but also depending on the topology. And then speed of convergence, as we have also discussed last time in other video, it has n square algorithm, n square message, uh, n square for the messages. It may have oscillations, but I mean this oscillations is something, well, it's not an issue actually. It's just something that can happen in the real life, depending on how we set up the routing cost calculation. And as well as for the dv distance vector, the convergence time varies. It depends on, as we have seen before, it depends on the topology, and also now it depends on how the link cost path change. If it changes from from good cost to the bad cost, or from low cost to the high cost, then it may have routing loops. Okay, because the routing just go back and forth, and it's also called the count to infinity problem. So in terms of robustness, what happens if router malfunctions or it compromised? um, as in ls link state, router can advertise incorrect link cost. Okay, yeah, because the only information that is, I mean, the link state relies on the link state or link cost information that is broadcasted. So if one router is compromised, then it may spread wrong idea of the link cost. And then as for dv, dv router can advertise incorrect path cost. uh, yeah, as we have seen before, if in case of link cost change from good to bad, okay, this is called the black holing. And each router table used by others, so if there is one error in one router, this error will be propagated through the network. So I think that's it for link state and distance vector algorithm. We'll continue about the routing protocols in intra ISP routing and routing among ISP in the next video. Okay, so stay tuned and see you again in the next video.